Okay, so let's talk about the properties that I already proved and some properties that I couldn't prove. I'll just list some properties. Okay, so some facts. Okay. Number one, lambda are real values. This was proved. Okay. And then number two, the values of lambda, there's some conditions. I hope I think this is right. If px is positive and wx is also positive, with these conditions are given, then there's an eigenvalue that's the least size, and then these are discrete values. And it goes to infinity. Okay, number three, the two FG non-trivial, non-zero, satisfying the Sturm Liouville with two different eigenvalues, right, are orthogonal. I.e., it means that if you integrate fx, and we're just going to assume that f and g are both real valued because we only have those examples. If it's complex value, you have to put a bar here. So fx gx times wx integrated from a to b would be 0 if f is a solution of this with lambda 1 and g is a solution of this with lambda 2, and those two eigenvalues are different. That's what's going to happen. And this was proved. Okay. Number 4, the eigenvalues are singular. This one is not so hard to prove. Yeah, I think I can prove it. So I haven't proved this yet, but let me talk about what singular means. Here, singular doesn't mean singularity of a function. Singular just means that you have only one eigenfunction per eigenvalue. In other words, if you have two functions satisfying this with the same eigenvalue lambda, then one must be a constant multiple of the other. Okay. So, i.e., two functions with same eigenvalue must be a constant multiple of one another. And number 5, the eigenfunctions form a complete set of orthogonal bases. Okay, now the fact that it's orthogonal is already proved, so what's really important is it forms a basis. In other words, if you have any function, so So let me elaborate a little bit. So say f1, f2, fn are eigenfunctions with eigenvalue lambda n. So f1 has lambda 1, I should say lambda 1, lambda 2, lambda n. Okay. Then any L2 function satisfying these conditions, but you know L2 functions are they don't really have to be continuous, so in that case this somewhat loses its meaning. So I'll just say it like this. Then any g of x with some conditions, so L2 with some boundary conditions. I can't say exactly what the condition is, but they can be represented as g of x equals the summation n from 1 through infinity of c1 f1 cn fn. Okay. So you can write down this as a infinite series of these things. And that's exactly what Fourier series means. So what was the Fourier series? When we had Sturm Liouville solutions as sine functions, we were representing the function as infinite series of sines, right? We also had the function represented as infinite series of cosines that was called Fourier cosine series. Sometimes we had both sine and cosines in the case when we had periodic boundary conditions. We needed both. Yeah. That was the Fourier series. Fourier Bessel series was when the functions were Bessel functions. Right? And you can also replace this by Legendre polynomials, right? And then show that it's gives you all the.
They're all the Sturm.
They're all Sturm Liouville in this. Yeah. So let me using that. Let me talk a little bit more about why this thing works. I mean, what does this mean? What's the implication of the Sturm Liouville problem? If we know all these facts, implication. See, just knowing that you can represent stuff is not enough, right? You have to be able to figure out the exact constants. And that's the question, how do we get it, right? And the way we get it is like this. Suppose g of x is cn fn x, n equals 1 through infinity. And we wanted to know cn. Okay. So then, think about the following. Then, g of x inner product with f k x. Let's do this. Think about what this would give you. Would be equal to
It would be lambda k.
No, there's no lambda here.
No?
Because we're not using L here. If there was L operator somewhere, we would be using lambda k, but that's not true. And then, because the inner product is linear on the first component, I can bring this all out and say what do we know about this? Usually what's that?
If n is not equal to k, there are orthogonal.
They're orthogonal. So that the inner product is
norm of k square.
Yeah, so usually their inner product will be zero.
Zero, yeah.
Zero, right? The only time this is non-zero is when
And
n is equal to k. Right? So that's when you get Cn just like that, okay? And then
I think that's CK, right?
Ck. Ck, thank you. Ck. Because
yeah.
when n is k, that's when you get this, right? And that's it. So therefore, what you get is, you get an important identity, which is that you get an important identity which says Ck is equal to G x fkx fkx fkx. And then you can find out the coefficients, right?
The same as the multivariable, you want to find the.
You can do similar things in the multivariable case. If you have a solution infinite series, and it depends on theta and phi and r, or theta and phi and t,
So
something
just
like
want to
that.
find a coefficient in some dimension.
Yeah, you just apply. In our case, we didn't use inner product. We did integration, right? So you integrate both sides by something, then suddenly all of these things disappear, and only some things survive, and you get this. Now, just to demonstrate that this really recovers things that you already know, let's just do it with this simple case where we had y double prime plus lambda y equals to 0, with y of 0 is 0, and y of pi is 0. What are the eigenfunctions? Y equals to sine x, nx, right? These are the ones that give you 0 when you plug in pi, right? So now, what am I trying to say? I'm saying that any function can be represented as some bn sine nx from n equals to 1 through infinity, right? Oh, by the way, n starts from 1. 0 doesn't give you anything non-trivial, so this is what you have, right? That's from Sturm Liouville theory. Now, how do you find Bn? According to Bn, Bn would be equal to f of x and then sine nx inner product divided by sine nx this, right? So let's see what that means. What does that mean? That means, first, what is sine nx? Sine nx. Well, our inner product is integration from 0 to pi, right? So you integrate from 0 to pi. And their wave function is just 1. So we put sine nx times sine nx, integrate from 0 to pi. That's the value of this inner product, okay? And what's that? That's sine squared of nx, and we can use the, what is that? We can use the double angle, half angle formula. That's like same as 1 minus cosine 2nx over 2, integrate from 0 to pi dx. And then this, if you integrate, you get sine 2nx, and then with some coefficient it goes away, because it goes up and down, and they cancel out if you integrate from 0 to pi. So you really get 1/2 integrated from 0 to pi, but that's a rectangle with base length pi and height 1/2. So what's the integral here? Pi over 2, right? Okay, and then what is f of x sine nx? That's integral from 0 to pi of f of x sine nx dx, right? And that's it. We don't know what fx is, so there's nothing to calculate. And you have to divide by this. Dividing by this is the same as multiplying by reciprocal. So we get the formula Bn equals to 2 over pi, 0 to pi, fx sine nx.
Exactly that.
It's exactly the Fourier sine series formula. Right? Now, then let's try something that we haven't done yet. So the other case, yes?
So why is that from 0 to pi? Can you explain that?
Oh, because it came from this one with y of 0 equal to 0 and y of pi equal to 0. So it's a Sturm Liouville problem on 0 to pi. Yeah. If this was from 0 to L, then in general it would be sine n pi over Lx, and the integral will be from 0 to L. Right. Okay? Alright, so now let's try something that we haven't done, which was the Legendre equation. So we see that only when it's L times L plus 1 you get some finite value thingy, and the solution of these, the finite valued ones, are the ones that were called Legendre polynomials, right? And we really didn't prove this because I only showed the self-adjointness for the case when you had specific values at the endpoints, but you can still show directly that this is orthogonal to one another. So let's say we have that, okay? And then so because these come from the fact that y of -1 is finite and y of 1 is finite, the inner product in this case is integration from -1 to 1. Weight function is still 1. This is your eigenvalue, okay? So, and we have, therefore we have two facts. We have integration of PL, PK, dx will be 0 if L and K are different. And then if they're equal, then it's 2 over 2L plus 1. That's what another thing that we proved, right? So with this, let's try to find out the formula for the Fourier-Legendre series. So Fourier-Legendre series would look like the following. You're trying to represent any L2 function over -1 to 1 as summation of, I'll choose AL, PL, X, 0 to infinity. By the way, P0 of X is just 1. When you plug in 0 here, then the constant function will be a solution. You can see that, right? Yeah. So the series this time starts from 0. And AL, by the formula that we figured out, it should be fx with PL divided by PLX, right? Okay. And we know that this is what? This is same as this thing, -1 to 1, by the way. Has to be this value, right? So it's going to be 2L plus 1 over 2, integrate from -1 to 1 of f of x times PLX. Okay. So that will be Fourier-Legendre series. So basically, if you came up with something nice to solve, and it turns out to be a Sturm Liouville problem, then you can have Fourier something series. So if I made such a thing, it would be a Fourier on series. Yeah. That's how you can do all things. Okay. These are called eigenfunction expansions. You can, if you have bases of eigenfunctions, then you have such expansions. All right, just one last thing about this thing. We really didn't solve. I mean, if you look at the solution of this, you might be like saying, well, you know that this is going to have polynomial solutions for these values because the infinite series terminates. But how do you know that there isn't any other cases where even if it's infinite series, you might have finite values at those two endpoints? And that's a fair question. You can think of it this way. If we missed some of these functions, then this series will no longer be complete. We'll have something missing. However, there's something else that saves us. PLX is degree L polynomial, right? So if f of x is what's called analytic, which means it can be written as a Taylor series over -1 to 1, you can definitely write them as sum of polynomials. So it's true for any analytic ones, but analytic ones are what's called dense in the set of L2 functions, and that means all the functions should be able to be represented like this. So in some cases, you may not be confident that you found all the solutions of the eigenvalue problem, eigenfunctions, but there might be some other way going around it and still say, well, we do have complete set, which means in turn you didn't miss anything. So that's another way to argue that PLX is everything. There's nothing else that satisfies these conditions.